materials side itself. Materials in adhesive joining. So basically the three types of the constituents which are used in these in the adhesive joining, like the some sort of the resins, or like say some kind of the polymers which are used. uh, then there we use elastomers, plus few fillers which are organic material basically. Idea behind use of these is like this helps to improve the shock resistance, improve the resilience, improve the vibration absorption, and the fillers basically help to improve the mechanical load carrying capacity, LCC, you can say, mechanical performance. And it also helps these the fillers when they are added in mixture to develop the adhesive joint. They help to reduce the thermal expansion and the contraction related things. So if it is more, certainly there will be cracking tendency and the reduced joint performance. So issues related with the because adhesive on its own will be expanding and contracting with the heating and cooling during the adhesive joining process. So that expansion and contraction tendency is reduced when the fillers are added. And as I said, some kind of the polymers which are used as a main joining component. There we use the two types of the like say the polymers. These are like the thermosetting plastics and thermoplastics. So we can, in short, we can say TS and TP. Okay, so initially talking with about the thermo setting type of the plastics. So here these basically these types of the resins, thermosetting type of the resins, they are of unique characteristics. Like whenever they are these resins, thermosetting type of the resins, when they are added either with the hardener or some kind of the catalyst. So in presence of the hardener and catalyst, these resins they undergo some kind of the chemical reaction, and as a result of these chemical reactions they get the desired strength and hardness, which you can say with the curing. So during the curing, basically the hardening and strengthening of these resins will be happening. So we can say here like curing, which is facilitating the these chemical reactions leading to the imparting or development of the desired strength. This curing is facilitated or accelerated by the application of the pressure, heat, or some kind of the radiations. So when kind of these radiations or the heat or the pressure is applied, the curing is accelerated. So, like say many times these get cured even at room temperature, but if the curing is done at little higher temperature of say 50 degree, 80 degree, 100 degree, so the time for curing purpose that is reduced basically with the increase of temperature. This is the simple thing. Okay, so there are the different types of the thermosetting and thermoplastic kind of the resins. So in case of thermosetting resins, once this reaction is complete, things have been hardened. See, so you cannot separate the joint. You can, and if you have to separate, you have to break the joint. Once it is broken, you see, even after the heating, you cannot develop the joint again. So this is a kind of a non-reversible process of the chemical reactions, which will be happening in one way only. Okay. On the other hand, so once the joint has been developed, you cannot, after fracture or breaking of the joint, you cannot remake it using the heating. That is the simple point. The thermoplastic is the another type of the resin which is used. These are basically the long chain molecular compounds. These compounds basically get softened when they are heated and they get hardened on cooling. Okay, the logic here is simple: heat, they will get softened; cool, they will get hardened. When you heat it again they will get softened. And this phenomena is coming from there because of the fact that there is no chemical reactions which will be taking place with the thermoplastics. Okay, so you can heat and cool as many times as you need, but when a high temperature exposure is given for a longer time, they thermally decompose or they get oxidized. So you can say with the prolonged heating of these causes the damage of these thermoplastics. Okay, so this is one broad classification of the resins which are used in adhesives as a thermosetting or thermoplastics plus elastomers plus fillers. Okay, again you see these resins are of the four types. Okay, the resins based on the way by which they behave, they respond to. Okay, as far as these the thermoplastics are concerned, these get softened when they are dissolved or solved with the organic compound, some kind of the organic solution. So they get softened, and when the solution is evaporated, they get hardened. So this type of the resins which get softened when they are added with some kind of the solution, organic solution, and they get hardened when the solution is evaporated. Okay, so this is this is what is typically a typical behavior shown by the thermoplastics. Okay, now coming to the types of the adhesives. Just a minute. Hello. हेलो. हाँ, मैं क्लास में हूँ, बाद में बात करूँगा ना. Okay, so now coming to the types of the adhesives, or like these resins, the way by which they respond to. uh, so one is, so there are four common types of the adhesives. One is solvent type. Okay, the second is hot melt type. Third is the pressure sensitive type. So what we can say here, the types of adhesives. Okay, the fourth one is the adhesives which will be undergoing through the chemical reaction type adhesives. Okay, so as far as the first one is concerned, the solvent type of the adhesives, here these thermoplastics, uh, these are produced in form of solution. Thermoplastics produced as a solution. Okay, and then when the solution having the solvent, when it gets evaporated, evaporation of the solvent, or you can say the drying out of the solvent, leads to the imparting desired hardness and strength. Okay, so this is one, the solvent type, and these are usually weak, so these are not used for the structural purposes, not for structural purposes. These are usually weak. The common type of the solvent type adhesives, where thermoplastics based solutions are prepared. These are applied when the solution is when the solvent is evaporated, either on its own or during the heating. These get hardened and impart the desired strength, but in general these are weak, so these are not good for structural purposes. Common examples of the solvent type of the adhesives are like neoprene is one, nitrile, NITRILE, and urethane, URETHANE. Okay, so these are the solution based solvent type of the adhesives. Okay, in hot melted type of the adhesives, these are a common example of the hot melt type of the adhesives include like polyesters. Okay, polyamide, ethylene, and vinyl acetate. So these are the hot melt type. So what we do, these adhesives in the molten state, these are applied on the surface of the component to be joined. The component and these molten adhesives are applied, and on the solidification you get on the solidification or subsequently on cooling you get the desired strength. Okay, like this. So hot melted type, these are also of the thermoplastic type of the adhesives, common examples are like polyester, polyamide, ethylene, and vinyl acetate. These are the adhesives which are applied in the molten state at the interface of the component to be joined, and subsequently on cooling you get the desired joint. Okay. Now we'll see the pressure sensitive type of the adhesives. These are like these adhesives under the effect of the low pressure or low load. Under the effect of the low pressure or the low load, these show the some strength when these are applied at the joint interface. But the joint produced by the pressure sensitive adhesive is also weak, so not good for structural applications. Okay. So the solvent type not good for the structural application. Hot melt type is also not good for structural application, and the pressure sensitive also not good for the structural adhesive structural applications. And these are used in form of like say the transfer tapes. And these are also used as a double side tape. Okay. The common examples of these adhesives include okay, I'll talk about these about these names I will comment little later. So next one is the chemical reaction type of the adhesives, and the chemical reaction type of the adhesives, these are basically thermosetting resins, and these are as I have said, these are activated in presence of some hardener or some catalyst for chemical reactions to take place, and in the presence of like say some kind of presence of heat, they get cured very easily and impart the desired strength. The common examples of the chemical reaction type of the adhesives include epoxy, the phenolics, acrylic, and the anaerobic, ANAEROBIC. These are the common thermosetting type of the chemical reaction based adhesives. Okay. So as I said, among these the structural adhesives are basically, so these are used for the structural application. So the thermosetting type of the adhesives which are based on the chemical reactions are used for the structural applications, and these offer the strength around 20 to 35 MPa. Okay, So you can say this is the kind of the strength that can be offered by the structural adhesive joints. Okay, it's and as compared to the typical weld joints, this strength is nowhere, but when it is used in combination with the conventional joints, then you get the multiple benefits. So maybe the adhesive joining is used in combination with the other joining processes. So this approach is good for hybridization of the joining purposes. Okay, so you can use with the weld bonding, you can use with the mechanical fastening, or even the laser welding or the friction welding, etc. So the number of other options are available for the hybridization purposes. Okay, now in which form these are used and what these are basically, I have talked about the number of types of the adhesives and their the specific compounds. Okay, so the forms in which these adhesives are used, forms of these adhesives. Okay, so one is the most common one is the liquid one. Okay, where it will be free flowing, the liquid. Sometimes it is just like thin and viscous, a syrup like of the liquid. Okay, these are also used in form of paste or some kind of the stick. This is just like in tube or the stick form. Then in form of like solids, and then it is also used in form of powders, and then you can say the films. Okay, now which form in which, so obviously depending upon the form in which the adhesive is available, it can be applied in different ways. So again, the choice of form in which this can be applied, it depends upon the first one, the choice of form, the shape in which available, whether it is in form of liquid, paste, solid, or a mastic, or the powder or film. That depends upon, one is the certainly the availability. The second one is that which method of application is available. Like obviously the different adhesive in different forms will be applied using the different approaches. What is the design of the joint? So you can say the design of the joint in which it is to be applied, then the production rate desired. Okay, like 10 units or hundreds of the units per hour kind of thing, or finally the economics certainly be affecting. So you can say the equipment cost, or indirectly the economics of the adhesive joining also you have to see. So if you the liquid form will be suitable in certain cases, maybe in powder form or paste form. So different situations, different parameters will be dictating the choice in different ways. So if it is about the form, choice of the form of the adhesive selection is concerned, we need to see these aspects. Okay, how these are applied. Okay, so application of the adhesives, these are like say use of the rollers. Okay, so just roll down over the roller is just moved over the surface so that the spreading of the adhesive is across the surface and it is uniform. Then application of the adhesive with the help of brushes. Then there is a spray gun. So you put the adhesive in liquid form, obviously, and then it is sprayed. Then trowels are also used for applying this one. So depending upon the liquids are mostly liquid adhesives are mostly applied with the help of the rollers, or this can also be applied by dipping the component into the bath of the adhesives. These can be applied using the brushes also. Okay. Then there are solid adhesives. How these are applied? No, solid adhesives. So to apply the solid adhesives, what we do, we heat the component on which the adhesive is to be applied, so that the solid adhesive melts, and then over it you apply the another component to be joined. So the solid adhesives may be applied in form of, like, say, rods, powders, pastes, powders, or these one will be brought to the molten state. So heating of the substrate or the components to a high enough temperature so that these melt. Okay, and then they get spread over the surface when they are brought in contact with the other component to be joined under pressure. Okay, on solidification you get the desired joint. Then there are films, the adhesive in form of films is applied with the help of, like, say, rollers, or these are can also be spread in form of sheet over the component. Okay, now the choice of the particular compound for the joining purpose, for adhesive joining purpose, depends on the metal to be joined. So adhesive selection, earlier it was form selection, now it is adhesive type selection, selection. So this depends on the type of the metal to be joined. Then there is a service requirement. This is very important. Apart from the component, the metal of the component to be joined, you have to see what are the expected service conditions. Okay, then what is the application method available? Application method means how the adhesive will be applied. That is about the application method available, and of course we have to see the economics of the adhesive joining. Okay, so as far as the service conditions, consideration of service condition in choice of the adhesive is concerned, you have to see that the type of loading. Okay, so there can be the four common type of the loads. One is tensile, shear, cleavage, and peel. Okay, so the for same joint may show significantly different performance for the different types of the load, or the way by which load is applied on the joint. In general, adhesive joints perform much better under the tensile and shear load, while they perform very poorly under the cleavage conditions, and further poorly in case of the loading in peel mode. Okay, so the peel strength of the adhesive joint is found to be only a fraction of the tensile strength of the adhesive joint. So efforts are always made that the adhesive joint is not subjected to the cleavage or the peeling load conditions. but it experiences primarily the tensile and the shear conditions. Okay, so on this I'll come little later as far as the type of the loading is concerned. So apart from the type of loading, we have to see the kind of the expected temperature range during the service. Then we have to see the environmental conditions, means because this is it's very sensitive to the exposure to the water or humidity or the chemicals. So you can say the moisture or the humidity is the another factor apart from the environmental condition aspect. Then the thermal expansion or contraction conditions. The other two aspects are like related with the toxicity or odorness if it is there. Then next one is the color match, color mismatch or match, as per the case you have to see. So the choice of the adhesive selection depends on the service requirement, the temperature conditions. Service requirements include the type of load, temperature range, environmental conditions, moisture, thermal and expansion expected, and the odorness or toxicity, and the color mismatch possible. So apart from the type of the metal to be joined, the application method and economics, the service condition plays a very significant role in the choice of the suitable type of adhesives. Okay, so what are those? So you know that the typical tensile loading in case of the adhesive joining happens in this manner. This is the pure tensile, where between the two components a butt joint is made and subjected to the tensile load. This is not preferred type of the adhesive joint. Okay, because the lap area or the joining area is very limited. The lap contact or the joint area is very limited, so the strength is very poor. But this is the typical tensile loading conditions. Okay, tensile loading conditions, and not, but this type, because of the limited joining area, this is not preferred. Okay, certainly the one which is preferred one is the lap joining. So in case of the lap joining, where you apply tensile load, but it experiences the shearing. So this you can say as the shear loading. Okay, in between the two, the adhesive joint is applied. Okay, when the two components experience the loading of this kind, where adhesive is made, joint is made between the two like this, and the subjected to the loading is just like crack opening mode kind of thing. Okay, so loading, you can say the P and the two components are joined like this. Okay, so the two components are these, the P1 or P2, and when these are subjected to the load P, so there is an opening tendency of the joint. This is known as cleavage type of the loading. Uh, for key cleavage loading, you see, as per the tensile load carrying capacity, um, the cleavage loading capacity is very less. So this tensile load carrying capacity is significantly high as compared to the cleavage load carrying capacity. Maybe like say if earlier it was having 40 MPa, then in tensile loading, then it may offer you 30 MPa, 25 MPa. But when you talk of the peeling loading under the peel conditions, so there what you find this kind of the situation. The two sheets are being joined like this, and this is the joint area. Okay, so the one load is happening in this manner and another is in this manner. Uh, so the this kind of when the adhesive joint is subjected to again here it's opening kind only, but this is more severe in terms of the loading. So the peel loading, again it tends to open up the joint, and the peel load carrying capacity is just a fraction of the tensile load carrying capacity. हाँ बेटा क्लास में हूँ मैं, बाद में बात करूँगा. So that is why, since the cleavage load carrying capacity as well as the peel load carrying capacity are very small as compared to the very less as compared to the shear load carrying capacity and the tensile load carrying capacity, therefore efforts are always made that the joint experiences the tensile and shear load only, and the cleavage and the peel loading is avoided. Okay, so this is the this was about the choice of the like the design of the joint should be done in such a way that you go for the tensile and shear rather than peel and cleavage loading modes. Now, as far as the parameters are concerned related with this one, so let us talk a little bit about the joint design only first. So what you have to consider, like the kind of the loading that will be there, and another important thing that is considered in the adhesive joining is the plastic strain capacity or capability of the adhesives. So adhesives will be able to undergo the plastic strain up to a limit. Thereafter, so that is what you can say as a creep also. So thereafter, certainly it will fail. And then you can say under the fatigue conditions, low cycle fatigue conditions especially, also you have to see that the creep of the adhesives. So you may find that there is some increased space, increased gap between the joint, especially when the plastic strain is more or the joint is subjected to the creep. So the adhesive is being subjected to the creep. So that will be uh, changing the relative position of the component. Apart from this, there are three other aspects about which I have to talk. That is about the adhesive joining parameters affecting the joint strength significantly, joint load carrying capacity significantly. This include, one is the overlap, the second is the thickness of the adhesive at the interface. Third is about the curing time, and the fourth one is the curing temperature. So the two are related with the curing and two are related with the, like, one overlap is the joint design and the adhesive thickness about the process conditions. So uh, starting with the overlap length. Okay, so your overlap length can be very small like this. This is one very short overlap length. or it can be little more like this medium overlap length. So in this case, so short, okay, so S you can say this much overlap, medium overlap, and when the overlap is really great, huge overlap, okay, like this. So the large overlap. Okay, so how does it affect the load carrying capacity of the joint? So you can say here strength if we mention, and overlap length in the x-axis. So initially when we are in the short zone, there is an increasing strength with the increasing overlap like this. So this is a short zone portion, short over length, and thereafter you will see that there is a change. So this section is almost linear. Thereafter there is a little change in the increase in strength is happening at the decreasing rate, and then it becomes almost constant. So the transition zone you can say as a, so the S1, then medium overlap length, okay, and then large overlap length zone, okay, S, M and L. So in case of the when the overlap length is more, certainly the plastic will be undergoing, adhesive will be undergoing through some kind of the plastic deformation. So you can say the plastic zone. And when the overlap length is significantly high, like in this L case, you see the strength becomes almost constant. Okay, so you can say this is known as constant load zone. Okay, how, what about this constancy in the strength? About that I will talk little later. So here the with the increase of overlap length, the constant load zone is achieved. In between we have the transition zone. Okay, so maybe it is good up to this stage of having the overlap length. Maybe this in a typical sheet of 1 inch width, and if you go with the overlap length of 10 mm, 15 mm, 20 mm, 25 mm, then you may find, say, this may be 10 mm, then this may go 20 to 25 mm. Thereafter, you may reach to the constancy stage. Uh, so overlap length, initially increase in overlap length increases the strength, and then it becomes constant. Okay, now there is one more aspect, like say this is the top view, okay, and this is the, let's say initially this is the overlap, and this is the another plate, and the joint is being developed. So you will be getting, say, particular load, tensile shear load. When you increase the strength overlap, again L1 will change to the L2, again L3, like this. So overlap length is increasing. Your load will also keep on increasing, L3, L4, L5, like this. Okay, so you keep on increasing the overlap length, your load will keep on increasing. This is very simple, this is not going to stop. But what is the gain in the increasing load for unit increase, for per unit overlap length, load divided by per unit overlap length? So what I am mentioning here is the L divided by the per unit overlap length. Hmm? Per unit length that is being given. So this per unit length basically becomes constant after reaching a particular value. So it means the you increase, and there is no further increase in the strength. strength means the load divided by overlap length becomes constant. So it is preferred that the joint overlap length is given up to this transition stage, and then it will reach thereafter to the constant load zone. It is just you can say, yes, one more thing. It is possible like if this side you have very thin sheet, this side you have thick sheet. Okay, this side 1 mm and this side 2 mm. Okay, so load carrying capacity of thin sheet is say just 10 kilonewton, and this side it is say 25 kilonewton because of the difference in the material and the thicknesses. Okay, it is possible that initially when you had a very small load length, it was offering you just like say 3 kilonewton, then 5 kilonewton, then 7 kilonewton, then 11 kilonewton. The moment your strength becomes 11 kilonewton, you will find that it has failed from the weak joint. So the point here is you can have the significantly stronger joint by having very large overlap area, but that may not be worth at all. That may not be needed for the given application, and you may find that the failure is occurring from the weak material, from thin sheets. Okay, so the important consideration is overlap and the load per unit overlap length like this. So once if this initially it will be increasing and then it will become constant. So wherever it becomes constant, that overlap length is basically used for the purpose of the adhesive joining. Okay, now if you are having the very thin, so thickness of the adhesive joint, thickness of the adhesive layer, so it can be very thin like this, just 200 micrometer, or say another one when you make it of 1000 micrometer at the interface, or it is 5000 micrometer. Okay, 5000 micrometer. If the thickness, this is the thickness, then you see the adhesive on its own will be dictating the strength of the joint. When it is thin, you will find that adhesive on its own failure tendency, because it is weak, so it will not fail when it is very thin, and there is a possibility like part of the failure may occur from the adhesive and the metal interface, part of the failure may occur from the adhesive, part of the failure may occur from the base metal side. So there are 3 or 4 possible ways by which these failures occur. Let me talk about that little bit. Let's say these are the joints. These are the components being joined. Okay. So now when you make the adhesive joint like this, okay, so the failures can occur. How the different ways by which the failures can occur. Let me choose color. Actually, I want to change the color. Let's see. Okay, so if you see, there are different possibilities. Your crack can occur from this location. This is one. Crack can occur from this location. Crack can occur exclusively from the adhesive. Crack can start from the another side of the, so the base metal A and the base metal B. So one, the failure of the base, this is one, base A, and if the failure is occurring from the B, then failure of the, you can say, or it can occur from this location as well as from these locations as well. So failure of A or failure of B. So I'm not saying which is strong, which is weak, which is thin and which is thick, but certainly there is a possibility of the failure from A and B both. Then the failure from the A and the adhesive interface, or failure from the adhesive and the B interface. Okay, and then the failure of the adhesive on its own. Okay, so when a proper joint is developed, you see, if you take the metal aluminum one side and steel another side, adhesive is not stainless steel another side, then adhesive is not going to interact with the two metals in the same way. You know, it will interact with the aluminum in one way and stainless steel in another way. Why? Because the surface impurities, surface oxides, the oxide thickness layers, all those are different, and and accordingly your adhesive bond strength on the aluminum side and adhesive bond strength on the stainless steel side, this is going to be different. So there are 5 failure locations from A, from B, from the adhesive and the A metal side interface, from adhesive and B side metal interface, that is this, and the failure of the adhesive on its own. Okay, so now whatever I have talked so far as the strength was concerned, in those cases we did not focus where from failure is occurring. But if you see, if your adhesive is extremely weak and it is very thick, then adhesive on its own will fail from this location, like say the C location, central location of the adhesive. And this is typically happening when its thickness is more. This will be offering you the lower joint strength. Before that, when the adhesive was interacting with the one of the base metal or other, in that case, so if the failure is from the interface of the base metal and adhesive, probably this is going to offer you the better joint strength. Okay, so this is so base metal nugget pull, those are the spot weld related failure, but these failures are little different than what we normally see in case of the spot welding. Okay, so with this, in this increasing phase of the strength basically corresponds to the interface, the base metal and the adhesive interface failures. And when thickness starts increasing, then we will say this is the adhesive failure. So basically the thickness up to a limit, you see. So actually the curve goes in like this, thickness and the joint strength. Okay, so there is an optimum. This optimum may be very less or on the higher side, maybe 200 micrometer, 500 micrometer. So that has to be optimized. Okay, it is said that the thickness of adhesive must be minimum one, but provided it is spread uniformly and the good uniform sound adhesive joint is developed with the minimum possible adhesive thickness. As far as the other parameters are concerned, let's say the load carrying capacity of the joint and the curing temperature, which may range say from say 50 to 150 degrees centigrade. So obviously for a given time of 30-minute curing, there will be increase in strength, and thereafter reaching a maximum level, you will find that the degradation will start. So you have to see that there is no degradation during the curing, and the maximum hardening and strengthening of adhesive is taking place. So certainly there is this is the time when hardening of the and chemical reactions in the adhesive will be taking place during the curing. And the same is true for your, so this was about the temperature. And say for a given temperature, for a given curing temperature, say 100 degrees centigrade, increasing time will definitely will increase, and thereafter again for the same reason strength starts decreasing after reaching to the peak hardening or peak curing time. Okay, so the load carrying capacity. So this is how, so what is important, like the thickness, the curing temperature and time, and the joint overlap length. So these need to be optimized. Okay.